Okay, shall we start?
Yes, go ahead.
Good. Welcome everybody to the first keynote talk. We are more than happy to have Srdjan Capkun. I hope I pronounced the name correctly. He is a professor in the Department of Computer Science at ETH Zurich, and also at the same time director of the Zurich Information Security and Privacy Center. He received his diploma, which is equivalent to Master of Science in Electrical Engineering, Computer Science, from the University of Split in Croatia in 1998, and also afterwards, let's say after 6 years, he received his PhD from the EPFL in Lausanne, and then he joined ETH Zurich in 2006, means that's 2 years right after his PhD. In the meantime, he was also a postdoc at UCLA, and also played the role of an assistant professor in the Technical University of Denmark. His research interests are in the system and network security. He focuses mainly on wireless security, particularly on positioning, let's say secure positioning. And he has also has some experience with the spin-offs related to the field of his research. He received also a prestigious ERC Consolidating Grant in 2016, 4 years ago, and at the same time he received the Fellow Award of ASIA. As I said, we are more than happy to have him as a keynote speaker. He is going to talk about his recent achievements with respect to secure distance measurement, from protecting car locks to securing contact tracing and navigation. Srdjan, the stage is yours.
Hi, I guess you can hear me, right? Thank you for this, for your kind invitation. It's always fun to talk about this research. So the topic of my talk is secure distance measurement. And I hope that I will excite you and make you potentially a fan of this topic. So let me start with a small example. So what you can see here on this video is a car theft in progress, right? But a little bit more sophisticated tech car theft in progress. Well, where you see one of the thieves here close to the house and the other one close to the car. And what they are performing is essentially a relay attack where one thief is exciting a key which is somewhere in the house, and the other one is relaying the messages between the key and the car, and they open the car and then they unlock the car. So this kind of a relay has been done already in 2011, and it's actually relatively simple. So a car and the key are playing a classical challenge response protocol with some random challenges and replies which are authenticated and confidential, and the adversaries are essentially just relaying those messages between two locations. So there is no notion of distance or time in this protocol, so it was rather simple to defeat it. And the same essentially happens when the adversary sits in the car. The same relay happens, and it allows the adversary to steal the car. The reason why this works is that passive keyless entry and start systems, they don't require any user interaction. Instead, what they someone's drawing on my on my slide, it seems. So it's what they do instead is that they as the key approaches the car. So as the car senses that the key is close, it will simply unlock. And the way that it does that is essentially based on the signal strength. Another example of where this kind of proximity is used in a security system is quite recent. It's contact tracing, and notably contact tracing system proposed by Apple and Google, where mobile phones are in this system transmitting pseudonyms, right? So they are transmitting some random identifiers that change over time. And if another device hears a random identifier transmitted by another device, it will essentially conclude that they were close by. And this proximity will later on be the basis for one device informing the other about infection. So if device A, for example, later on, or if the owner of device A later on is infected and gets a test, then B and C are going to be notified of this infection. And this is inherent to any contact tracing system, no matter how you build it, right? I mean, this proximity is translated into a risk of infection. And if an adversary, like what was done in this research, not very surprising, right, pulls a wormhole between different people and their devices, then clearly the adversary can convince many people that they were close to each other. So once that the infection is being announced, then many people would be notified. And clearly these people were not close to each other because instead someone pulled a relay between them. So that's a very nice example of a sort of recent attack on a system that has just been announced. I mean, the attack is in some way a denial of service attack. I don't believe it's going to have that much of an impact, but it nicely illustrates how distance translates into some functionality within the system. And if we cannot trust this distance, we will not be able to trust that functionality either. Another scenario is if you imagine two cars approaching each other and measuring their mutual distance and deciding when to brake based on this distance. If an adversary can influence this distance measurement, in this case, the adversary could enlarge the distance that the two cars observe, unlike in the previous examples where the adversary was reducing the distance that the devices observe. So in this case, if he enlarges the distance, the cars would be convinced that they are still further away than they are, and at some point they would crash without noticing. Clearly, this is here. Clearly, I'm assuming only distance measurement is being used to detect the proximity between cars. One could use many sensors, but the question is how reliable is distance measurement on its own to provide you with such functionalities. So if you cannot trust it, you probably cannot build a system on top of it. Which drives me to the following point. So ranging is a nice functionality, right? But we actually need to build ranging systems that are hopefully provably secure from all logical and physical layer attacks. I'll discuss physical layer attacks in more detail in a moment. And in such a way that we can build all the applications on top of this, right? So the security of these systems should not depend on the context or the attacker's ability to potentially follow the victim or inject some signals at a certain speed, but not at some other speed, or the ability of the attacker to buy a software-defined radio, or to generate or to buy some fancy oscilloscope and so on. So we should build these systems in a similar way that we build our encryption, meaning that it's independent of the context in which it is being deployed. And this would be an ideal outcome, right? So what are the ranging techniques that are currently available, and what's happening in this space of secure distance measurement? So surprisingly a lot. So non-time-of-flight distance measurement systems over the last 10 years have been shown to be insecure. So a lot of them, like RSSI measurements and phase measurements and so forth, have been successfully attacked in various environments, and we know that we cannot rely on those. However, it is quite timely that time-of-flight systems are emerging now, and they provide much better robustness to attacks. And so we already have two different standards being developed. So one actually approved a month ago based on ultrawide band technology, and the other one in development in the context of Wi-Fi that that are developed for secure ranging. So ultra-wide band 802.15.4z has been approved now in August 2020. It has been proposed some years ago. We were involved in this standardization process. And it has been proposed specifically to enhance 4F and 4A standards, which were standards for ranging with security, with additional security features. And in the context of Wi-Fi, we have now developments. So there is a standard called AZ, which is a next generation positioning standard, where we, from the documents of the task group, you can see the efforts to secure this OFDM-based ranging system. And in 5G, what we can see are first academic proposals towards secure ranging. So we see a sort of evolution, or better say, there is now more awareness of the need to propose something in this space. There is also a lot of movement within the industry. So FIRA is a consortium of large companies that aims to standardize and deploy ranging, so fine-grained ranging, and also Car Connectivity Consortium is pushing for ultra-wide band ranging. So both FIRA and Car Connectivity Consortiums are actually mainly pushing the ultra-wide band based solutions, which are short-range solutions, right? You can see them as kind of Bluetooth like solutions in terms of the range, whereas Wi-Fi and or especially 5G is something that can be deployed on a wider scale. What we can also observe is that ultra-wideband is also being increasingly deployed in commercial products. So if you own an iPhone Pro, you can see that, you can probably notice that it has an ultra-wideband technology. I don't think that it's so widely used, but an ultra-wideband chip, so U1, has been deployed in iPhone Pro, and currently it's used for some sort of an enhanced AirDrop functionality. Now the security of this system is not fully open. I'll discuss this a little bit later. So it seems to be using an HRP mode of 4Z, and its security is sort of not very clear. So it's for those of you doing attacks, it's probably a fun target to look at it. We are certainly looking into it in my group. Another deployment of ultra-wideband, which is maybe a more clear use case, is in passive keyless entry and start systems. So now we know that ultra-wideband 4Z LRP mode, which is another mode of this ultra-wideband standard, is already deployed in passive keyless entry and start systems of new Volkswagens and Audis, and I'll say more about this mode. And there are also announcements now of ultra-wideband based contact tracing bracelets. So this particular chip is built to prevent those kind of relay attacks that I showed at the beginning of the talk, meaning to provide robustness against distance reduction attacks by the adversary. So the adversary should not be able to convince a key fob and the car that they are closer than they actually are. So if your key fob is in the house and your car is outside in the driveway, the adversary should not be able to manipulate this distance measurement process to shorten this distance and to essentially convince the car that you are within a meter or 2 meters distance from the car. This is an example of a board that we have in our lab, which is an ultra-wideband system that does this secure distance measurement. I'm showing you this video just because people often wonder what kind of precision or latency these systems have. So here you can see this system in practice. So you can see the distance there as my student walks around in real time, right? So you can see that it's fairly fast and relatively robust to this environment. So how do these systems work? At a logical layer, time-of-flight-based protocols are fairly simple. So especially in the most common scenario, which is the most common scenario is that the car and the key fob, or the verifier and the prover in this case, are mutually trusted, right? They're built by the same manufacturer. They pre-share a key. They can agree on some cryptographic material, and now they can perform some sort of a challenge response protocol and measure the round trip time of flight. For the adversary who sits in the middle and tries to reduce this measured distance, all these bits that are flying around, like this NV and MP, these challenges and responses, are essentially completely random and unpredictable. And so one at that level, especially when we talk about this particular setting, the protocols are rather simple to analyze. There are many other attacks and frauds in this space, and if you ever read protocols, distance bounding protocol papers, a lot of them are actually based on some assumptions that don't really hold when you try to implement these systems. So there is a bit of some of these papers, let's say, do not reflect the reality of the implementation of distance bounding protocols. And I'll try to explain this through the next slides. And this is because of the physical layer, right? So if we are trying to transmit some messages, right, we want to transmit a challenge, and we want to or transmit a response, we can choose how to encode these bits into symbols, right, which are wireless symbols. In this case, we see a short symbol here, so single pulse per bit, right? So we have one ultra-wide band pulse that is of one polarity that is transmitted as one, and then another polarity that's transmitted as a zero. And now you can imagine a longer symbol as a set of several pulses, right? It can also be in any shape, right? It can be an OFDM symbol, it can be anything else, but you can imagine that now the short symbol being a single pulse and longer symbol being multiple pulses. In this case, they have a pretty predictable shape, right? You know how bit 1 looks like and bit 0 looks like, and this is what the adversary also knows. What one needs to be also aware is that we are also limited in these systems by regulations. So if you look at, for example, ultra-wide band systems, we have a peak power limit and we have a mean power limit. So we cannot transmit at an arbitrary peak power. So we can either transmit over, let's say, 1 millisecond, we can either transmit fewer pulses at a higher power level, or we can transmit more pulses within the same time, but at a lower power level. And this is what these mean and peak power limits tell us. Right, so you can either decide to kind of spread your energy over many pulses, or you can focus that energy into a single pulse if you want, like shown in this short symbol here, right? You can transmit only one pulse, and maybe that's fine for you. So one pulse per bit. So why would we even transmit multiple pulses? Well, because even if you transmit all your energy in one pulse, this only gets you so far in terms of the distance and in terms of the neighboring noise and interference, right? So even if you have a limited power within, let's say, 1 millisecond, what you can do, you can transmit over several milliseconds. You increase the latency, but you will still aggregate the energy, and you will therefore then extend your range, right? So you're trading the range for latency. So in principle, you're going to accumulate more pulses or more samples over a period of time in order to detect a bit. So in this case, you will sum up across these blue or green pulses. So we need to aggregate over several pulses, and this will increase the robustness and range. But clearly, this is vulnerable to an attack, right? So, and this attack is a consequence of having, in this case, predictable symbol. So if you initially want to measure a distance, right, the key fob is going to send this message at a certain time, and now each pulse is going to pulses are going to be received in the same order and with the same spacing by the car as they were sent. But an adversary can do something else, right? The adversary can actually inject this message earlier, and this is how it works. So the adversary can now initially create two pulses that do not really look like either a pulse, a positive or a negative pulse, just some garbage, and inject this garbage within these shaded blue slots that you see here. And then once that the adversary figures out which pulse the transmitter has actually sent, he can predict the rest of the pulses that he needs to commit to, right? And what he does is he injects then the appropriate positive or negative pulses, depends on which bit was sent. And what the receiver is going to do is what the receiver should do, which is sum up the energy in these four slots in order to obtain a correct bit, right? And the energy overall is going to be positive, and therefore the car is going to conclude that this is a bit 1, which is a correct bit that initially the adversary couldn't guess, but managed to infer from the first pulse. And but this correct bit is going to be received, as you can see here, earlier, with an earlier time of arrival than it should have been, right? So we have a time of flight system that has been violated by this early detect late commit attack. So initially, it might seem that we have a performance security trade-off, right? That we can only achieve security if we have a single pulse, because a single pulse is, 1-2 nanoseconds long, and this means that even the fastest possible attacker could potentially cheat at most by 15 to 30 centimeters. And we might conclude that longer symbols are inherently vulnerable to these kind of manipulation attacks. I mean, early detect late commit is not the only type of manipulation, but it's a good example of what an adversary can do. So, but at the same time, we need longer symbols for performance, and as we have seen, for range and robustness. So the first thing that comes to mind, because we are security people, is let's randomize the symbol. This is actually not the nicest thing to do, right? There are a lot of there are reasons why symbols look as they look, right? In terms of bandwidth, and also in terms of detecting these radio signals. It's good to know what you are. I mean, they're encoded in a certain way to let's say be robust to environmental noise. And so transmitting something that looks random is not as efficient as transmitting something that has been developed as a part of a code that should reduce interference or noise. So, but even simply randomizing pulses actually doesn't really work. So, and the reason is shown on this figure here. And this is, so let's assume that the adversary simply guesses the first pulse, right? So he guesses the first pulse. This is the red pulse that you see here. And now he's right. So he guesses with 1/2 probability he's right. At this point, he could even stop, because out of 4 pulses, he has guessed 1, and maybe that's sufficient energy to fool the receiver. Now, how does he know that he was right or wrong? Well, because he can see later on, a few, let's say 100 nanoseconds later, he will see a pulse coming from the legitimate transmitter, and he can now see if he was right. If he was right, he can essentially stop the game. If he's wrong, he can continue the game. In this case, our adversary decided to continue the game, and he was wrong. So here he was right, here he was wrong. So some sort of autocorrelation is not going to be good. So, but what he can play in addition is he can also, in the next attempt, he can, for example, double his energy, right? He can double the power of the pulse that he transmits, hoping that this time he's right and he can overcome the previous failures. And he can continue playing this game, right? In this last attempt here, he transmits at 4 times the power of a legitimate pulse. And if he succeeds there, he has essentially won the game. And he always knows pulse by pulse whether he has won this game. So, so just randomizing pulses and then doing some sort of cumulative sum over the energy doesn't really work well. And so the autocorrelation here, or any kind of spreading that you might have in mind, actually doesn't work in this context, cannot be made secure. And ironically, the more pulses you have, the more chances you're giving to the adversary to guess, right? So you're getting worse over time. And this is something that here, we work in security, so we need to consider best case for the attacker and worst case for the user. And this makes this problem of secure distance measurement even worse, right? Meaning that when you're designing a secure ranging system, we are talking about scenarios where someone is carrying a mobile phone, or there is some drone flying around, or a car moving. And this means that all the nasty things in terms of noise and the channel and so forth is something that the victims or the legitimate parties, they need to consider and they need to account for, and their system needs to be, the thresholds within their system needs to be set in such a way that the system still works under those noisy environments and doesn't trigger and doesn't reject distances frequently, right? So you want this, you would somehow want to tolerate some errors, let's say pulses not being received correctly and so on, because we are accumulating the energy over individual pulses, because each individual pulse cannot be resolved by the receiver, right? Given the sensitivity of the receiver and given the neighboring noise, the noise floor is such that it's hard to make a choice based on one pulse. So you need to aggregate the energy over multiple pulses, as this figure here shows, right? But for the attacker, we need to assume a perfect channel, right? He can get close to the car and he can put his antenna literally on top of the antenna of the car. He can shield this environment from noise, so he has a nice channel and noiseless environment to the victims. Maybe in this case not to the key fob, but we have to assume, if you're building a secure ranging system, it should be secure against in any environment, including the environment where literally the attacker hooks to the antenna of your sender and your receiver, right? This would be the ultimate attacker, right? So what would be the solutions that work? So we were thinking about this, and what we realized is that autocorrelation based solutions don't work, because they're still, because there the attacker can still successfully know when he failed, and also guess pulses that he continue guessing pulses. If he failed, then he can continue if he or not continue when he succeeds. Instead, what we can do, we can essentially do, we can randomize the symbols in time, in the sense that in the way that's illustrated here. So if you have two symbols, bit 1 and bit 0, what we can now do is we can reshuffle them. And now what is going to be transmitted, the transmitter will be what you see below here, where the adversary would not know which pulse belongs to which symbol, right? In this case, it would be easy to infer that, because we have only two bits and the polarities are known. But if you have multiple bits, then this breaks, right? So now the adversary no longer knows which pulse belongs to which bit. So he doesn't know if he has won that bit. And since there are multiple bits that you have to win in this game, right? Let's say that the challenge consists of 64 bits. You have to win all these 64 games, and you're playing them simultaneously, and you don't really know which game you're playing, because you don't know which pulse belongs to which bit. And so this is now the probability of the attack will reduce with the number of interleaved bits, and the probability of the attack will actually increase with the number of pulses per bit, as we have discussed before. Another solution would be to look at the variance of a set of pulses that you receive. So we know that in ideal conditions we are supposed to see pulses which are well formed, and we are supposed to see, let's say, 4 pulses that roughly have the same power. And if the received signal deviates from that, in the sense that the variance of the pulse energy is too high, then we could potentially say that this is an attack. And of course, this needs to be different. I mean, this profile of these errors needs to be different from the expected noise, right? So the attacker's goal here would be to create the correct bits to increase the mean, right? Because you need to increase the mean energy that is accumulated, right? But at the same time, he wants to minimize the error, meaning reduce the variance, right? And these two goals are essentially conflicting, right? Because the longer that he plays the game and he injects his pulses, the variance will increase. But of course, also his chances, he needs to continue playing in order to increase the mean, because he's injecting energy, right? As he adds the energy, he is also he's increasing the variance, but he's also increasing the mean. So the increase of the mean is tied with the increase of the variance, and so we can essentially, based on this observation, build a statistical detector that will now look at the profile of that and look at the profile of the expected noise and see if this can be used to detect an attack. Another solution that has been proposed in this space is actually proposed within the 4Z standard. So it's HRP variant, which is a so-called scrambled timestamp sequence. So the idea is, and a lot of these systems actually have a preamble. So there is is to measure a distance from 2 parts, right? One is a preamble, and this preamble can be public, and is also, it also has good correlation properties in the sense that it's some sort of a code, let's say a ternary code, which can be nicely acquired by the receiver. And what is done is that we measure the distance based on this preamble. And then there is this scrambled timestamp sequence, which is essentially a random set of pulses, which is generated cryptographically and doesn't have such good correlation properties. So it's not that great for distance measurement, but it could be used then to verify the time of flight. So essentially what happens is that you estimate the distance based on the preamble, and then you estimate the distance based on STS, and they should somehow match. And for each of these, it's not perfectly clear because implementation is up to the individual company, but these two autocorrelations need to match. So there is an autocorrelation done on the preamble and on STS, and they need to match. Now, one needs to analyze these numbers carefully. So we actually created scenarios where this particular test fails. So we can attack this kind of a system successfully under different assumptions. And so the security of this is actually quite questionable and not well understood, I would say. So if I now sum this up in the context of a recently adopted standard, so 8.15.4Z, so the ultrawide band standard, what you have is you have 2 modes. Currently, one is LRP and the other one is HRP, so the low rate pulse, so a mode in which you transmit fewer pulses at a higher energy, and another mode where you have a high rate pulse, so you transmit a lot of pulses at a lower energy. By a lot, I mean you transmit thousands of pulses. In order to do ranging, you might be transmitting 10,000+ pulses to measure in essentially a single packet, right? So in terms of low rate pulse, in terms of its security, this mode actually can use a single pulse mode. So this means single pulse per bit. So if you transmit 64 bits, you transmit 64 pulses, and that's fairly secure. I mean, you don't get essentially better than that, because you get 1 bit of security per one pulse that you transmit, and Or in this mode, you can use this interleaved symbols, so UWBPR, in order to enhance its range, essentially, right? And there is currently an open security specification which is in the standard. For the high rate pulse, you cannot use single pulse mode because given the power that is being transmitted per pulse, right? Because of this because of the high frequency of pulses being transmitted, you cannot transmit at a high power, which means that essentially, you would not be able to detect individual pulses unless you're extremely, extremely close, right? So you, at any reasonable distance, the receiver would not see individual pulses and therefore needs to aggregate and do some sort of autocorrelation, right? And in terms of implementing variance-based detectors or UWBPR, they seem to be inefficient in terms of the implementation. This is now one of the areas of study, because one issue is that with such thousands of pulses, you essentially need to keep track of many pulses, of many values that then you need to aggregate into different bits, and this might not be the most efficient thing to do. Similar thing with the variance, right? You need to build a circuitry that then calculates this variance over this large number of pulses and across these two sequences. And some HRP implementations, they use STS, as I already mentioned, with autocorrelation. But for efficiency reasons, this autocorrelation is actually done over, so the search for the peak is done over a limited time range, which also contributes to the security issues here. So we still don't have open security specification here, because what the standard specifies is what you see here above, right? So meaning the number of pulses and the format of the packets, but it does not tell you how to implement these security mechanisms on the edges, right? On these transmitters and receivers. And this is a bit disappointing, because one would expect that in 2020 that one would have a bit more open push for security in products and standards. And now, if I take a step back, after working on this for a while, we were thinking, okay, is there something that ties these things together? And I would say that, and we sort of put it all under one umbrella, right? Because what we are in fact concerned here with is the message time of arrival, and what we want to secure is in fact message time of arrival, right? So we want a type of a code, we want a type of an encoding at the sender that allows the receiver to verify the integrity of the message arrival time. So you can see it as a message, as kind of equivalent to the message authentication code, just in the domain of time, right? So we can assume that we have 3 algorithms. One generates the key. Fine, the transmitter and receiver have now a shared key, and then we have this MTAC algorithm here, which will generate, based on the message that you want to transmit, will generate an encoding, and this encoding could be similar to what we have seen, like single pulse per bit, or interleaved symbols, or variant, or can incorporate something in the message so that variance-based detection works better. And then we have a verify algorithm, which takes a received message and decides whether the message has been received without being shifted in time. And this is something that's a kind of an interesting way of looking at it, and sort of unifies what we several of these approaches into at least under a single umbrella name, right? I cannot give you a formal, this way of thinking about it still doesn't give you a formal way to verify whether something is a message time of arrival code or not, but at least it defines what it is, right? So you know what to work towards. So I still have some minutes left. So in terms of Ultrawide band. I think we are now at a sort of mature state of this topic. There is still a lot to be done, in terms of improving the performance and the security of this topic. But there are products out there, there are standards out there, and we need more research to understand. Someone's not muted. More research to understand this space. So I invite you to look into these standards, and they will probably evolve over time. So I invite you also to contribute there, because from the side of academia, at least, we were the only participants in that in some of these meetings. So it would have been nicer to have seen more faces there from the academic community. Now, moving, and I'll try to use the remaining 5 to 10 minutes to another challenge, which is that ultra-wideband is a short-range communication technology, and it's going to remain such. And one of the reasons is that these ultra-wideband systems, they use anywhere between 500 megahertz and gigahertz of spectrum, and that's pretty nasty, right? So that spectrum is, and they sit within the spectrum that other technologies might use as well. And this means that the output power of these radios is quite limited. And so it would be good to also provide secure ranging within the context of technologies that will be longer range and that will be standardized to be deployed on a wide scale, such as 5G, right? And so we would, our goal there is to have a single hardware for communication ranging and also low latency, longer distance. But 5G currently, it's an OFDM technology, and it complicates time of arrival estimation and security by using first long symbols, and also by using coherent receiver design. So let me give you an idea of where we are heading in this space and what we are currently proposing, and hopefully it will excite you to also do something in this space. So first, if you look at the physical layer of 5G, so OFDM symbols, you can see that no matter what, so if you're not super familiar with OFDM, it's essentially a technology that leverages many subcarriers that are simultaneously used to transmit many bits at the same time. And but what is maybe important to see is that the maximum bandwidth of this system is around 400 megahertz, which results for this kind of OFDM symbols in a symbol length of 2 microseconds. Now, if you compare this to the symbol length in ultra-wideband, the symbol length in ultra-wideband is anywhere between 1 and 2 nanoseconds, which means that now each nanosecond of a symbol length gives the attacker the ability to cheat on the distance by 15 centimeters. So microseconds is quite a lot. So we cannot have symbols that are microsecond long, but still in OFDM we do. So how do we get around that? And another issue is a carrier frequency offset, which can be used to manipulate this distance estimation. Namely, unlike ultra-wideband, where we have preambles that can be used to, essentially synchronize the sender and the receiver to a particular time slots. Here in 5G, we don't have that, and there are reference signals that are being sent from one device to another in order to correct the carrier frequency offset, in order to correct the IQ diagram and enable proper demodulation. And if the attacker can manipulate this, he can also do the manipulations of the time of distance measurement. So we came up with a system that does something funny, and I will explain in more detail only this first part, so the short symbols. So we build a system that should work against enlargement and reduction attacks, and first creates short symbols out of long OFDM symbols. And second, it provides two additional checks on the signal integrity using variance to check for signals, to check for manipulations within the transmitted signals, and also data integrity, which essentially corrects for the for this CFO manipulation. So how do we? So maybe most interesting is how do we achieve short symbols? So we achieve short symbols by, so in OFDM on the left side, what you can see, let's say, regular operation of OFDM, where data, this +1, -1, and so on, is each data bit is encoded is modulated by one subcarrier, right? And so if you have different data bits, your final OFDM symbol is going to look like something as weird as you see here, right? So each of these bits is essentially modulated on top of a narrow band, right? And now what we did in our system is that we use the same data bit for all the subcarriers. Now, if you do that, what you effectively achieve is that, well, you're summing up across all possible frequencies, all of these subcarriers, which in the end will result in some sort of a pulse, right? Narrow pulse. So the symbol time, which was 2 microseconds, will now be essentially 1 over the total bandwidth that you have here. So we will bring the symbol down to a few nanoseconds, and this is pretty cool because we are in effect, simulating. We can now translate some of the results from ultrawide band into OFDM, and without changing the hardware, because this is pretty legitimate operation of OFDM, right? We can encode the signals in this way in any hardware that supports OFDM in 5G. And now the time of flight estimation is going to be pretty standard. So the search for legitimate signal is going to happen at the receiver in a conventional way. So any receiver that wants to process this can do this. Also, of security and privacy of smart vehicles, where vehicles would move through cities and would then be and where there would be a localization infrastructure which would confirm or which would be able to provide secure positioning for these vehicles, so that vehicles could autonomously navigate and potentially tie these locations to their identities, which would be in some onboard black boxes of vehicles. So this is something that it seems now, with these developments in secure positioning, we can finally start doing. And of course, I have many papers where I predicted things that will never happen. And so as far as prediction goes, I'm not sure that my score is that high, but at least in this case, it seems to be heading in the right direction. In terms of future work and summary, I think there is a lot of work to be done in this space. First, in analyzing and also improving secure ranging techniques, proposing new ones. There are a lot of other modulation schemes and systems that, at least in the research community, I don't see anyone has been tackling, and it's a fun topic. Also, so most notably 802.11, 5G, these efforts just started, and anyone's input is clearly welcome, I'm sure, right? We need more discussion. We will need more efficient implementations. Currently, we do have ultrawide band chips that are extremely low power, so their power consumption is at the level of Bluetooth Low Energy. So there are efficient implementations, but there is more to be done across these different technologies. Clearly in deployment, and we need certainly more tests and see what this can be used for. So in summary, it's an exciting area, which somewhat started with protocol level distance bounding and was kind of let's say detached a bit from reality, but now it's getting more attention and relevance, and probably a lot of these distance bounding protocols need to be revisited in light of these recent implementations and results, because we can get security only when we look at these systems holistically. Finally, the acknowledgement slide, right? I mean, this a lot of things that I mentioned also resulted from a collaboration of a number of people that you see here, and many more on different publications. But let's say these people helped with the results in these slides, and yeah, it's probably good to, or at least I want to thank them for all the effort, and I'm happy to take questions.
Many thanks for the interesting talk. I already see 2 questions in the Zulip chat. Actually, the third one just posted. The first question is by Kevin. He asks, in the case of GPS transmissions, there are multiple transmitters and a single receiver. Are there opportunities to apply secret sharing techniques to improve the security of distance calculations, distance measurements, based on the received signals from multiple transmitters, so that a minority of participants cannot misrepresent their actual location?
Oh, there's a lot of that. So, so I'm not sure that I fully understand the context, but in the context of GPS, so clearly there are already secret spreading codes being used for military GPS. So yes, that can be used. So to try to protect those codes from abuse or manipulation of signals, right? That is not really perfect, because no one prevents you from recording those signals and then replaying them at some later time to a receiver. And if the receiver doesn't see any other signals, it will probably resolve a location that you want, because the security of GPS as well is not in the content of the signals that you transmit, but rather in the relative time of reception at the receiver, right? And I didn't understand this last part in terms of misrepresenting location, because GPS receivers only receive, so they can essentially claim any location that they like later on, unless you use some other technologies. So I didn't mention this in this talk, but I believe that broadcast systems like GPS are inherently insecure, right? I mean, you cannot secure such a system. You need bidirectional communication for that, of the type of distance bounding protocols. But yeah, I'm open to discussion on that point.
Okay. Kevin, if you want to unmute yourself, if you need to discuss more, I think we have time for that.
I'm not sure that I have enough knowledge to really expand the conversation. I mean, we used to think that broadcast encryption couldn't be secure, but you know, our minds have been changed by new protocols developed there. It just occurs to me that if you expand outside of GPS, for example, and you look at multiple automobiles transmitting to each other, then, you know, if a single automobile cannot misrepresent its location because there are other automobiles confirming the communications from that single automobile, they can override any misrepresentation from a single automobile, perhaps. That was the kind of thing I was thinking about.
Okay, so we worked on, so sort of in this talk, I talked only about one particular scenario. What you're talking about is essentially something called an untrusted prover. So where someone is trying to cheat on its own location, right? And we do have protocols for that, and we do have implementations for that, where we can actually verify a location of a device that's claiming a location. And this can also be done using distance bounding protocols. And if you drop me an email, I can point you to a couple of publications that that show how this can be done, and you can actually prevent cheating of a single device by using distance bounding protocols. So this verification can happen. However, it requires multiple. It requires essentially bidirectional communication. I guess what you are referring to is more like a time difference of arrival, right? I mean, one transmitter would be transmitting beacons, and then others would be doing TDOA to verify its location. That is a bit of a, I mean, that would fall apart if that transmitter would use directional antennas and selectively delay its signals. Now, again, you could say this might not be easy in the context of cars, and I agree, but if you're looking at a really powerful attacker that can selectively, send its signals with different delays in different directions, then time difference of arrival would not work as a location verification technology.
Thank you. We have another question referring to your slide number 17. If you don't mind resharing your slides or screens.
Sure, I'll just do that. Slide number 17.
Yeah, the question is, okay, you are at.
Okay.
Yeah. The question is, why not randomize the time delays between two consecutive pulses instead of the amplitude as shown in slide 17?
So randomizing the time and not the, well, the reason is that essentially all of these systems. So sure, I mean, one answer would be yes, you can do it, but the reality is that most of these systems in their implementation, they're trying to be efficient, trying to identify these pulses then when they're being at the receiver would be a bit of a chaos, right? I mean, you could, I mean, if you know where to look for these pulses, I guess you could do that. So you could, so I think in principle, this idea would work. So yes, you could do that. How these systems work typically is you have a preamble, right? And so all of these ultrawide band systems, you have a preamble, the preamble is known, it's good for acquisition. It's like with most radio systems, you need to know what you're looking for, right? So you're looking for a fixed preamble. And when you find this preamble, you essentially know in which slots the pulses of the payload are going to come, right? And this is why, and this is relatively then easy. This is then efficient to implement and to build such radios, because you know where you're looking for these pulses, and especially if you're also locking to a phase, and because these pulses might, the pulse polarity might be encoded in the phase, then you're looking for particular slots, and this works quite well. I would say that in principle, time spacing between pulses could be randomized. I would need to see what is the granularity of that. How would then the receiver be able to lock to those particular slots? But yeah, why not? Why not? You would still need to, however, you would still need to randomize so you should not do only that, right? You would still need to have the attacker should still not know which pulse belongs to which, well, maybe not. I have to think about it. It might actually work as well. Yeah.
Shouldn't be a receiver and the sender synchronized based on this randomized delay? They should Absolutely. Be right.
Yeah. This I assume that's what you meant, but I'm just thinking whether there is an additional mechanism that you need. So whether the attacker, whether you still need to confuse the attacker in terms of which pulse belongs to which bit. I don't know if you need that in addition or not. I have to think about that, but yeah, it's an idea.
Okay.
Next
We have
question.
another. Yeah, there is another question. Actually, this person who asked thanks you. Another question is that you have shown how you can transmit short symbols through an OFDM transmitter, but is that really the hard and crucial part? I thought the hard and crucial part is to make sure that the receiver is not sensitive to energy outside the short time window in which the pulse is meant to be present. How do you achieve short pulse shaping or gating in the OFDM receiver?
So in the OFDM receiver, well, because you are in fact receiving a short pulse, right? So in the end, the symbol time is long, right? But all the energy will be within this short pulse, right? So the ability of the attacker now to predict, given that the ability of the attacker now to predict essentially which bit has been sent will still be limited, because the bit that we are sending is still an encoded bit. So it can be any, because the amplitude and the phase are still encoded in this pulse that we are sending, right? So which means that the attacker still cannot guess which bit this is, right? So I'm not
Are
sure.
you not opening yourself up to another late commit attack? Because I can now, as the attacker, put some energy at the end of the symbol that will look similar to energy that you thought was contributed by your sharp pulse at the beginning of the symbol.
Well, if you do that, then you're not going to get the same type of a symbol, right? I mean, what we are also doing is, so I mean, we can discuss this offline, but I don't think that should work. But that's a good question. I don't see how this would work. I don't think you will get the same symbol. What you might shift yourself in the IQ diagram somewhere else as a result, right?
Okay.
I mean, right? Because you need to hit the right bit, not only the so a single. So you're talking about manipulating one of the subcarriers, right?
I'm just worried there is a Fourier transform between what I send and what you analyze. And the Fourier transform makes sure all the samples depend on all the other samples. So can I not do something devious towards the end of the symbol that you will interpret as information at the start of the symbol? And that I committed late, but you interpret it as energy that has arrived early.
So
for the other side of the Fourier transform.
No, but our receiver, right, is not decoding this in that way, right? So the way that, so I guess you're assuming a certain type of decoding in the receiver. But I assume
it's a normal OFDM receiver, because you set the transmitter to the normal OFDM hardware.
Yeah, okay. So the receiver cannot be a normal OFDM receiver, because OFDM, so 5G still didn't specify how this ranging would be done. So you inherently have to essentially do your own time of arrival. You need to implement time of arrival functionality, right? And so you don't have to go through this process that you just mentioned, but you would be detecting this pulse sort of differently. But it's a good question. I mean, it's essentially a good question to be careful in that decoding. If you would use a standard OFDM receiver, whether you would have some vulnerability. That's a good question.
Thank you so much, Srdjan, for a very nice presentation and the talk and the good discussion. We run out of the time. Kevin has another question, but I'm pretty sure he can ask you offline. One more time, I would like to thank you. That was an honor to have you as a keynote speaker. We have now the coffee break. And